Hello. This is Big Log Entry 132, and it's about noon. I've been reading quite a bit. I've been looking everywhere because, again, I'm reacquainting myself with a lot of random quantum physics concepts because now I believe that my understanding, again, I've mentioned my understanding of quantum physics, it tends to be more abstracted. I'm not really appreciating some of the history behind it, so I'm looking at the history of quantum mechanics a little bit, and just like the general evolution of quantum mechanics from the 1900s when Einstein was doing the photoelectric effect, and now I don't remember exactly what the photoelectric effect insinuated, than like them throwing particles into a material, and then this material radiating. It has a particular intensity or flux of energy, and this flux of energy is change of energy over time, which is power. So it's like a power over a particular area. You have to think of it over an area because this is a material. It's not a dt, or dA. So a dA would be a point in two dimensions, essentially. Let's not talk about that. Yes. So I was looking at that, and I just I was looking at the ultraviolet catastrophe because I remember I was doing a lot of reading, and I was looking at the Schrodinger, the Paul Dirac equation, relativistic Paul Dirac equation, or just a Dirac equation, I guess would be the best way to say it. And it's filled with a lot of do they have tensors? Maybe. I think if it's pertaining to, if you're adding general relativity to it, then yes. And it's, when it says relativistic, I'm assuming it's both general relativity and special relativity. I think it's just special relativity. And then we account for general relativity outside of the system, and then we add that to it. I'm assuming is probably the best way to do it. Because it's just a curvature of space-time, where you can think of it as a manifold or whatever, and well, you can talk about all that. Maybe actually they did add they probably have like the special relativistic one and the special relativistic Dirac equation. And I went down a little bit of a rabbit hole because that means I have to understand. Just to understand all this, you have to understand quite a bit of math, and I've heard of manifolds. You hear from pop sci a lot and everything, and I don't really. I wouldn't say that I have a good understanding, but manifolds, of course, are used in general relativity, and these manifolds are just like warping of space time and whatnot. And then geodesics, from what I can see, of course, I kind of know some of this stuff. I know of a lot of the terminology that's used in general relativity, but I wouldn't say I understand the math as well as I'd like to. So I do have to delve into that. Luckily, I have a book on that too, and I also have the internet, and I've been writing a lot of notes. I was just generally writing a mind map. I like mind maps. Mind maps are good because also these mind maps are kind of inspired by the Socratic method, and I kind of just I write down like the highest abstraction, which is a manifold. Well, actually, the highest abstraction for me. Because I think of when I think about higher abstractions, I think of like the thing, and then everything else that represents that thing is like another layer, right? And the layer of the concept of the Dirac relativistic equation involves quite a bit with, first understanding the Schrodinger equation. You don't have to understand it necessarily, but you have to apply it to the Paul Dirac equation, because the Paul Dirac equation also involves general relativity. And also it involves special relativity. So I understand special relativity, I understand Lorentz transforms to a degree. I mean, I understand the math behind it and why it needs to, because, when you look at special relativity, due to the postulates that require this to happen, is that, so again, special relativity is a theory based on two postulates, very simple postulates. One is that no matter how fast something is going, the speed of light will look the same from it. So the speed of light is the same no matter what inertial reference frame that you're looking from. And the second postulate is that no matter what inertial reference frame that you're looking from, the laws of physics still hold. They're still constant. And from these postulates, they created special relativity. To account for these postulates, time and space has to be dilated. So that's why they have these Lorentz transformations where it's transformed space based off of going from a non-relativistic to a relativistic point of view. You have these, you can call them operators, and I guess these operators are called Lorentz transformations. And these Lorentz transformations are depending on how fast this object is going. So there's an input, which is the velocity of the object, probably, and it outputs a linear. It's a linear transformation too. It's a linear operator, or linear. You could think of it as a linear function. You could think of it like that. So you can think of it like an object going really fast, and then you're looking at the from your perspective. It's hard to look at space from that perspective, and it's hard to look at time. But you know, you can imagine that you have these grids or whatever, you know, that you see in like punky or what's the other word? Something punk, like Blade Runner kind of stuff, you know. And then, or if you're like listening to like techno music, you have like these, you know, how they have like the, like 1970s kind of stuff with the grids and things moving. And yeah, I don't know. I just think of it like that. It's like kind of like a pinkish hue to it and everything. It's kind of, I don't know. This is what I'm thinking of in my head, and it's a weird example, but yeah. So I just felt like talking about this because I tend to I like translating the the abstractions of my head into English at times, because it helps me understand it more and be able to explain it in layman terms, sort of layman terms. But yeah, so yeah, it's a linear. But the Lorentz transformation is a linear transformation or function. You can think of it as a function. Linear transformations. What are linear transformations? Basically, linear transformations have. You can compare to a derivative. Derivatives are linear transformations, actually. So a derivative. So basically, let's say that you're imposing a transformation on an object, and this object has, it can be segregated through the plus sign, and the plus sign is like it has a distributive. So linear transformations have a distributive property. Not only that, these linear transformations also have a commutative property with multiplication. So like, let's say you have an alpha in front of it. This alpha is a scalar, and then these objects could be scalars or vectors or matrices or whatever, and then you have a linear transformation outside of it. So you have this object which is linear. This object, it imposes what? I'm not sure if these objects have to be quote unquote linear. I think they do. But from my perspective and what I've learned from linear algebra, I'm assuming that that's the case. These are all linear objects that are linearly transformed. Yeah, so it has those two properties, and actually derivatives supplement those criteria. They fit those criteria. And yeah, because if you think about, if we're taking standard calculus, these derivatives are, I think I like thinking of linear operators. It's just like a way of abstracting into a perception of like a different like layer. It's another layer of abstraction that people think about. Imagine abstracting abstractions all the time. I guess that's like what everybody does. You see it everywhere. You see it in just everywhere, because abstracting abstractions help out with simplifying and compacting information to a better place without taking so much space, I guess would be a good way to say it. For computer science, and also English as well does that a lot too. And I guess mathematicians kind of do the same thing, and I'm kind of doing the same thing because I like to that's how my head thinks. I like to start from the top and then go down, because I like knowing where I'm going, and to a degree, okay, it's hard to tell. It's hard to say. I know it's more that I just like having control, and that's how I think about things. I like to think at the highest layer of abstraction and then extrapolate downwards. Not the highest layer. I can't really say that. At a particular layer that suffices for what I think is my level of understanding. And yeah, that's why I'm looking at fields, because I understand fields, sort of. Anything beyond that, obviously, I don't understand the standard model. I still don't really quite understand spin and what that entails. There are a lot of things I don't know. Of course, like anybody else, we all have our limitations. But yeah, anyways, so what was I saying? I was talking about, I was just talking about abstractions and whatnot, and linear transformations. Why did I go? Oh yeah, because I was talking about special relativity and how I'm actually backtracking from what I like, where my brain was branching from. Special relativity and its need in the relativistic Dirac equation, as well as general relativity, and you have to understand tensors. And I also, I believe these tensors are linear objects as well, which means they have linear transformations imposed on these linear objects, and these linear objects. The thing is with tensors, again, there are certain qualities that must maintain variant or invariant under certain transformations, and that's what tensors entail. The abstract version of it is that tensors contain objects on its diagonal, potentially, or I'm still not 100% sure, but they tend to hold certain information in them that is invariant amongst certain linear transformations. I'm not necessarily sure if it's all linear transformations that can be imposed on it. That's another interesting thing. I'm supposing it is, because, if you think about, you can think about space, right? I guess since we're on the topic of tensors and space-time and everything, so space-time is I think the reason why we use tensors is because space-time can be kind of placed into a three-dimensional, or let's just think about space. I guess we don't have to talk about space. Okay, if we're talking about space-time, then we can add it could be a fourth-dimensional matrix, but it's a tensor. It's under matrix is a superset of tensors, I think. I don't know. Anyways, I have books on that, so whatever. I think the tensors are seen in that way, and these transformations have to hold under certain things, because again, like the laws of physics have to hold from certain transformations, and general relativity is not an exception, I'm assuming. Now, I can't really think of I guess you can think about like the speed of light. So like, let's say the speed of light is going straight, and then sure, there's a certain amount of time, but then if you add a manifold to it, the manifold stretches space and time. And no, that's probably not a good example. I wouldn't know, actually. I actually can't think of conceive of why tensors are used in like manifolds, and well, okay, if we... That's a good question. I think there's an example that I've seen with tensors. There was an example involving shear force. I think there's something with shear force that involved tensors. I can't quite remember why they used tensors for this, and I'm assuming there's information that is withheld in it that doesn't change. Some kind of constant, I guess. I don't know. Anyways, I need to look into that. I'm seeing a lot of synchronicities. Not every time, but mostly every time I look at the time and the clock, and not just the time, but the recording time and all that, and I see a lot of synchronicities. I don't feel like talking about that right now, though. Yeah, but my current conception of tensors are just matrix invariants, or matrices with certain invariant information, no matter the set of all linear transformations that can be induced on this particular object. Yeah. So I could be wrong. I'm gonna have to look at chin. Oh yeah, I was also looking at covariance and contravariance. It's also important in understanding space-time, and I saw that too. I saw covariance and contravariance in the Dirac's equation, because I think, well, I don't remember the ordering, but there's a superscript for either covariance or contravariance, and then a subscript for either covariance and contravariance. I just don't know which is which. Yeah, so I also have some misunderstandings with the Hermitian, which is linear algebra. And an adjoint, I remember learning about adjoints in math once, and I just don't remember what it is, so I had to look into that. And then I was looking at Noether's theorem. Noether's theorem is basically providing a relationship between symmetries and the conservation of force in systems. Or just conservation laws, not conservation of force. There are conservation laws that pertain to something force. Conservative forces, yeah, of course, because if you think about conservative forces, you can think of a conservative force field or whatever. So you can think of 2 points, and no matter which way you go, it's still going to be the same force implied of it. That's basically what a conservative force is. Easiest one to think about is a linear force field just going one direction, all the vectors are the same. And then, so that means, if it goes in this direction and that direction, well, I mean, another thing is that if there's no, like, initial force implied outside of the field, then obviously it would just go straight, but at a constant acceleration, I guess. Yeah. So, and obviously that's a conservation of that employs a conservation of energy, of course. Doesn't imply. I don't know what I'm saying. The energy is also the potential energy is the same, I guess. That's why they call it conservative forces. So no matter which path it takes, the total energy of that given system or slice of that system, because I guess it would be considered system because it's a field, and then like yeah. Anyways, I don't feel like talking about all the specifics in the terminology that could be used. I think I want to be very, very precise with how I talk about things. That's why I try my best to use the right words, but at the same time, I double back on how to say it properly, so there isn't any ambiguity behind it. I guess I like to be precise with my vocabulary and how words are defined and how to use them in proper settings and contextualized areas. So yeah, and yeah. That's basically what I've been doing. All of this branches just from looking at the Dirac equation. So, but at least the reason why I like it this way because I have a particular motivation in mind, and I know this is going somewhere as opposed to going to school. It doesn't feel like you're going anywhere. They know where you're going, but you don't really know where you're going, right? So it feels better from this angle that I'm taking. I've done this multiple times in real life as well, not pertaining to concepts, but real life, where I throw myself into kind of iffy situations and then just kind of adapt as I go and figure it out. It makes it... Maybe I'm a bit of an adrenaline junkie. I don't know. I like to think I'm somewhat of an adrenaline junkie. I just like not things changing constantly. I like things changing constantly that are in my control, that I can tangibly perceive to an extent and foresee in intentional chaos, I guess. Not chaos that is imposed from the outside world that's out of my control. If that kind of makes sense. Yeah, so I do like chaos though. It has to be chaos induced by me. It has to be induced by me, not from the outside world. That's what I'm trying to say. Yeah, so tensors. Yeah, tensors. I really need to look at tensors and what the hell contravariance and covariances and all that crazy shit. Oh man, what the fuck is this? What the hell is this? 33, 31, 32. What? Oh no. Oh right. What? I'm looking at a diagram of this. This is confusing the hell out of me. Oh, vector matrix. Okay, tensors actually have an inherent structure that's different. Very different. What the hell? 8 by... Oh, is it... I guess it starts off as a three-dimensional object? Like this one's R 4 by 4 by 4. 4 by 4 by 4. But then I guess there are different ways to... Like these... I mean, the cool thing is about... I don't understand why they use tensors. They just seem like three-dimensional arrays that happen to have information embedded within it that is kind of encoded within it that tends to be separated in a block formation inside of it. It's just a different way of encoding, organizing information within matrices, I guess, is another way to say it. Like a three-dimensional... Okay, what's a good way to say it? A tensor can be a three-dimensional matrix, but a three-dimensional matrix not necessarily can be a tensor, is basically what it is. Okay. I'm gonna have to... I've looked at practical... Like years ago, I looked at practical applications of tensors and what they're used in, but it didn't have to do with general relativity or the manifolds and encoding information within manifolds. But I can understand why they would do that because. But these tensors, are they in? Another thing is, are these tensors embedded? Are these, like, if you have a point on a manifold, right? Each point on the manifold is a tensor, maybe. How would that work? I mean, like, I don't know. I'm not going to think about that right now. Although seemingly different, the various approaches of defining tensors cover the same geometric concept using different language and at different levels. You see, that's why they make it so. They're multi-dimensional arrays is how I've always thought about tensors. And then, like, the thing is, like, I think computer scientists always calls them, tensors. I think there's a confusion between computer scientists and mathematicians on what tensors are. I think mathematicians have a different conception of what they are. Yeah. Oh, the Kronecker delta. Dynamic matrix. Why do they? Isn't the Kronecker delta in, at least in the instantiation of matrices or from the matrix perspective, just an identity matrix? It's just a generalized way of that. Okay, whatever. I've seen Kronecker deltas before. I don't know. Multilinear maps. So tensors can also be seen as multilinear maps. Okay, there are just so many ways to think of tensors. I guess the simplest way is from a geometric standpoint, and they're quote-unquote multidimensional arrays. And then the other way, I guess you could think of it from a linguistic perspective. They're multilinear maps. Multilinear. Is that it is not apparent from the definition that the defined object is indeed basis. That's okay. Basis independent. Although it is possible to show the transformation laws indeed ensure independence from the basis. Okay, so they have a differential, quote-unquote, differential geometry perspective of tensors. It's to define tensors relative to a fixed finite-dimensional vector space V. Relative. Okay. That's interesting. They call finite-dimensional vector spaces as fixed. Tangent space. Defined as a multilinear map. Okay, so it's a dual vector space. They didn't say that. V is the dual space, which I believe is what is it, like it's a vector space, but it also has like a dual set of what is a oh man, I'm so out of I'm out of practice when it comes to linear algebra. I remember hearing this too. A dual vector space, or just dual space for short, consisting of all linear forms on V, together with the vector space of a structure of a pointwise addition and scalar multiplication by constants. I guess okay, that's what I was basically saying. Like doesn't every vector space have a dual vector space, which is its transformations? They call it a dual vector space. I would call it a dual space because that's just misleading to a degree. Of all linear forms on V. In mathematics, a linear form is a linear map from a vector space to a field of scale. Why do they... Oh, God, they have so many different ways of calling these things. That's why I hate... Okay, whatever. Wikipedia can be annoying at times because I have a conception of a particular terminology in my head, but then they use like apparently linear forms are linear transformations, basically, or functions, linear functions, basically. I don't know. It's just like they have so many ways of saying it. Yeah. Anyways, I guess that's the downside of English. Whereas that's why I like math, because there's a like when you write down an equation, as long as you understand the rules of math, everybody knows. Everybody's on the same damn page. And there's, I think, I don't know. I can't really think of a good example of. I mean, I guess like if you think about linear algebra, like you can think of like matrices as linear transformations, which then can be functions, and then these functions can also have a direct homomorphism. There's a direct homomorphism between the function and the matrix. So, yeah. I guess we do that in math too, but at least we kind of explicitly say that, and we actually have a name of, I guess, in English too, they have homophones, or not homophones, synonyms. It's just, I don't know, I guess they're less, the best way to say is that there are less synonyms in math than in English, and I know of a lot of synonyms, of course, because I've been speaking English my whole life, but still, I just get annoyed. It must be nice to ride through these fields upon the horse of true mathematics, while the like of us have to make our way laboriously on foot. Laboriously. I don't know, I said it like that. Albert Einstein said that. Anyways. Oh, yeah. This page is huge. What page am I on again? Oh, tensors. Oh my goodness gracious. There's so much stuff about tensors on here. I wouldn't even know where to start. Which is, yeah. I'm not going to worry about all the perceptions of tensors, and I'm going to use tensors in the way that I see fit, and that's from a manifold standpoint. Manifold, or understanding Einsteinian gravity. So, yeah, but right now, I at least I understand the general structure, what tensors are and what their purpose is to a degree. Wait, oh, NASA has an introduction to tensors for students of physics. Oh my god. Whoa. Yeah. Yeah, I have to look at covariance and contravariance. I did take a break too, just so you guys know. I hung out with my friend yesterday, and we had a fire, and we don't have a lot of interests. We have a lot of interests, but our interests are very different. He likes architecture and history, and I tend to like more STEM-oriented stuff, so every time we talk about things, we tend to learn things from each other, and that's actually a nice relationship to have with somebody that doesn't have the same interests as you. It's nice to talk to other people about your interests too, because you can learn more about your interests by talking to other people. But at the same time, I want to increase the aperture of my mind, so I don't like just having to talk about my interests. I like to hear other people's interests, and I actually enjoy people a lot. I like understanding their motivations more than anything else. That's why I always ask them. I was like, why? And people take it by offense when I ask them, like, why are you interested in this? No, I'm generally interested in your interests, or at least why you're interested in it. And I'd like to see your perspective of why that can be interesting. So maybe I'll be inspired to be interested in it as well. You know what I mean? Now that hasn't occurred with history and architecture, though. I don't really care about those things much. Yeah. So what is all this? I don't know. I'm just like mindlessly scrolling through a random page about tensors and all that. Yeah. So I have a lot of mathematical research to do. I had to look at Hermitians and adjoints and all that. I think these. What is the joint? I don't remember the Hermitian or the adjoint. What is the Hermitian? Is that a star? No, I don't know. Oh, Hermitian matrices? What the hell? Okay, so it's just a kind of matrix. So they're it's just a kind of matrix with certain properties, obviously. So matrix and a joint. What's a joint? Man, I remember using this. I vaguely remember. I remember. Well, this course that I took in college, I was not paying attention half the time because it was very dull. Because they were just talking about mathematical methods for physics, and goddamn, that can be. And this guy was going through all of the computation. I was like, why? You don't have to go through all the numbers, bro. It's like they just. I mean, if he didn't do that, then there wouldn't be any purpose of the class. And it was actually based off of like just practicing computation on a fucking whiteboard and writing it out. I was like, God damn it. The last time I did that was when I was going over Gaussian elimination in college, and I was like, yes, I had to do it just to get through the course, and this was all under linear algebra and linear. I don't know. Gaussian elimination is like, what is it like? It's a way of like, the purpose behind it, I think, was to solve it a set of equations. That's what Gaussian elimination is, and they solve these equations by, of course, creating a ladder effect, I think. So it creates a ladder effect by first. What's the best way to say this? Well, basically when you solve a linear equation, you can actually encode it into a matrix, and then it times its inverse is equal to its identity, and you're trying to get to the identity, and the inverse happens to be the inverse matrix to that which creates its identity is the set of solutions for it, or some shit like that. I don't know. Oh no, sorry. It's not that. Sorry. Maybe it is. I don't fucking remember. I forgot what I did. What connection I had for that. Now I'm trying to remember what I did on those things, because I vaguely remember that. What was the method that was used? I think the method was to make, well, you have to cancel out. So basically is that you look at this is a square matrix, and then you look at the diagonals of the column. You start at the top. I think it's probably the best way. You can either start, I think it's better to start at the top and then go diagonally, and then you'd have to cancel out its components. So you'd have to scale them, these matrices by a certain amount to then cancel these out. And these transformations somehow held, or something. That I vaguely remember this, but they were multiplied by. You can replace the row vectors by a scalar transformation of these. These are vectors as well, so you can replace the row vectors by a scalar transformation of it multiplied by some scalar that happens to cancel out its other components within that column, to then create a bunch of zeros, and then the diagonals are the solutions to the equation, I believe. Yeah, they would be the solutions to the equation. So it could be like x1 to like 5 or something, and this would be a 5 by 5 matrix, and that simply would hold due to just I don't know how to explain it. I guess it's seen as. Now you can think of it from not looking at a matrix point of view, but you due to properties of the matrices, they happen to hold for whatever reason. I don't know what that means. But it worked. Yeah, it works. It works. That's all I can say.